Hello everyone, welcome back to CP 517-WS Digital and Computer System Architecture. This is part 2 of lecture 8. This part will talk mainly about very long instruction word or VLIW. So the problem we've been looking into of Tamasulu's algorithm of speculative execution, we really want to say is how could we get CPI below 1 or even lower, right? If we want to get the CPI below 1, we cannot do that if we only issue one instruction per cycle, right? Because that's the bound. So what if we do multi-issue processor, such as we statically schedule superscalar with dynamically schedule superscalar? For static schedule one, we rely on proactive methods. That is, before we do execution, we figure out how to schedule. While dynamically scheduled superscalar, we basically use hardware to do that. Very long instruction word is the way that we do statically scheduled superscalar, right? Two types of superscalar processes issue very number of instructions per clock, use in-order execution if they're static executed, or out-of-order execution if they are dynamically scheduled. Very long instruction word processor issue a fixed number of instructions formatted either as one large instruction or as a fixed instruction packet with the parallelism among instructions explicitly indicated by the packet, right? So when we do VLIW, we basically already let the processor know how it goes, and the dependencies are explicitly indicated. So this is a simple comparison between static superscalar, dynamic superscalar, superscalar with speculation, and VLIW. We can see that for issue structure, the prior three of them are dynamic. And then VLIW is static. Hazard detection, use hardware. Scheduling, we do static, while the other do dynamic, and this one even do dynamic with speculation. And then VLIW, primarily using software, right? So for VLIW, we primarily do software-based hazard detection, and then scheduling we use static. The distinguishing characteristics is that superscalar with static, you do in-order execution. Superscalar with dynamic, we do some out-of-order execution, but no speculation. It's like Tamasulu's algorithm. Superscalar with speculation, we do out-of-order execution with speculation. VLIW, all hazards determined and indicated by the compiler, often implicitly. Okay. So they basically are done at very early stage before execution. All of them typically are used by some computers. Like for example, static superscalar used by MIPS and ARM. Well, dynamic superscalar, because it's an incremental stage of one stage later is the speculative, right? So people typically use speculative, such as the Pentium 4, MIPS, IBM Power 5. For VLIW, typically people use like ATEM or embedded systems, right? Very long instruction word. Each instruction has explicitly coding for multiple operations. For in AMD IA64, we call each group a packet in transmatter grouping called a molecular with atoms as operations. Atoms. Okay. Trade-off instruction space for simple coding. Long instruction word has room for many operations. All the operations the compiler puts in the long instruction word are independent. They can be executed in parallel. For instance, we have two integer operation, two a floating point operation, two memory references operation, one branch operation, so we can put all of them together. It takes 16 to 24 bits per field. Taken together, we need 168 bits wide for this instruction. Need compilation, compiling techniques that schedule across several branches. We can use this example as an example for our next explanation, right? So in last lecture, we talked about loop unrolling, if you guys still remember, for the for loop of subtracting every element by a value, right? So, and then we store it back. We do loop unrolling to achieve like 3.5 cycles per iteration. This is already very good. But the thing is, after we do loop unrolling in very long instruction word, like we do loop unrolling first, and then we do very long instruction word. You see here, assuming you have two memory accessors, like memory operators, and then you have two floating point operators and one branch operator. So it takes 9 cycles for us to finish this many instructions, which previously takes 14 clock cycles. So can you use 15 minutes to solve this equation? How many loops do we unroll to achieve this goal? And how many registers do we use in this unrolled and then VLIW instruction string? And the number of clock cycles per year, what is the number of iterations, cycles per iteration? How's the hardware resource usage ratio? Like some of them at this cycle, for instance, right? You only use 50%. Well, at this cycle, the usage is 0%. Similarly for them. So what is the hardware resource usage ratio? Okay. Can you use 15 minutes? Pause the video for 15 minutes to solve this problem. This is the solutions. So we need to unroll in total 7 loops. Okay, here we have unrolled 4 loops, right? Here we have to unroll 7 because you have 7 load and 7 store. How many registers do we use? You have to count here. R1. So in total is, I think it's 13, not 3, not 1.3. So you have F0. Okay, F0. Do you use F1? Oh, really? And then F6, F10, F14, F18, F22, F26, and then we also have used F2, F4, but I finished all of these. And then I finished this. And then F8. Okay, F12. F14, F12, F20, F18, F20. Right. 22, 24. $28. 4, then 8, then 12 included already, 16 not included, this was not included, so here, and then F20 included, F24 included, F28 included, and then R1, right? So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we use in total 16 registers. Okay. Comparing to here, we use how many registers? F0, F6, F. So we have, let's do this count 1, 2, 3, 4. Okay. F14, F0 is recounted, F0, F2. F8, F12, F14, 16, F4, F8, F12, counted, R1. Okay, in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it 10? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So from 10 to 16. Right. So it's 1.6 times more usage. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Sorry, 17. So that is 1.7 times more register usage, right? And then number of clock cycles. Oh, I see. So the result is like this. Number of clock cycles is 1.3. Okay. So it's what, 9 cycles divided by 7, right? That is 1.3. Hardware resource usage ratio. We have in total how many hardware resources components used in 9 cycles? In total is 1 to 5, 25, 45, sorry, cycle operations. And then how many we used? 7, 7, 7. So 21, 22, 23. So it's 23. So that's 23 of 45. It's almost half of them are wasted. Right? Okay. Let's count this. Okay, I did a recalculation about the number of registers. We see here F0. Okay, F0, F2, F2. F4, six, 8, 4, 6, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So you can see it's from 0 of even numbers until 28. It's in total 15 elements, right? Registers. I think that's clear. If we don't count this R1, right? So that's 15, matches what I had before. Okay, the problems with the first generation very long instruction word is it increases the code size. Generating enough operations in a straight line code fragment requires ambitiously unrolling the loops, which whenever VLIW instructions are not full, unused function units are translated into wasted bits in instruction encoding. They have to be operated in lockstep, no hazard detection hardware. A stall in any function unit pipeline causes the entire processor to stop, since all function units must be kept synchronized. Compiler might predict function units, but caches are hard to predict, right? So when you have cache misses, then all the instructions has to be waiting until that cache miss being fulfilled. And then binary code compilability. Pure VLIW, different number of function units and unit latencies require different versions of the code or compilations. Increasing instruction fetch latency. We can predict next instruction address, send it out before decoding instructions. We can send the PC of the branch to branch target buffer. When match is found, we predict the predicted PC's return if the branch predicted taking instruction fetch continues at the predicted PC. This is what we discussed in prior dynamic branch and static branch prediction section of lecture 7. We can also do instruction prefetch, integrated branch prediction, and instruction memory access and buffer. For integrated branch prediction, branch predictor is part of the instruction fetch unit and is constantly predicting branches. Instruction prefetch is per the name. We prefetch the instruction and deliver it to multiple instructions so that every block cycle we can integrate that into branch prediction, right? Instruction memory access and buffering, fetching multiple instructions per cycle. Value prediction is something very interesting. So we attempt to predict value produced by instructions. This is interesting because it could be sometimes the value is not changed for very frequent time, right? Value prediction is useful only if it significantly increases the instruction level parallelism. There are researches, I remember recently was one paper been doing this for some benchmarks. The related topics is address aliasing prediction. That's what I mentioned, memory aliasing, right? Address aliasing prediction is both more stable and simpler, since there's no need to actually predict address value. We only need to predict such value conflict, like what I mentioned before, A plus 8 versus B plus 20. They might have the same value, but they have totally different base addresses. So if we do value prediction, it's easy it's very good because we only predict the value. This value is 25, and we predict this value was to be 25. So then it's easy, right? Makes the aliasing prediction easier, and this is where the value prediction being frequently used. Okay, that's that for part 2.